Good afternoon. Today we will be studying Theorem 6. In the earlier session, we have studied Theorem 5, which was for non-homogeneous linear recurrence relation with constant coefficients. Now, in this session, we'll study Theorem 6, which is basically, so if you remember, while we were taking particular solution for Theorem 5, we were just assuming what the solution might be. So if you remember, I had taken for 2n, the particular solution can be Cn plus d, where both C and d are constants. And for 3 power n, actually for 7 power n, which we did in the earlier problem, I took the particular solution as C into 7 power n, where C is some constant. So in this theorem, we will actually see how we get those particular solution for both of those where we have a polynomial in n or nth power of a constant. So in theorem 6, f of n is either nth power of a constant, that is either 1 power n, 2 power n, anything like that, or it is a polynomial in n, 2n, 3n, 3n plus 2, n square plus 1, such that, or it can be both product of the polynomial of n and the nth power of a constant. So let me just write it over here so that it is understood. Whenever f of n is product of a polynomial of n or nth power of a and nth power of a constant, then we will be using theorem 6. So basically f of n will be 3 power n, 5 power n, anything, and along with that it may be multiplied with 2n, 3n, or simply n or n square plus 1. We will see a few examples, but for now you have to remember where we are using theorem 6. Theorem 6 is being used whenever we have f of n in such a way that it is a product of a polynomial of n or nth power of a constant. Now, so we'll see the general form of theorem 6. Suppose an satisfies the linear non-homogeneous recurrence relation an is equal to I is equal to 1 to k ci a n minus I plus f of n, and f of n is I is equal to 0 to t b t minus I n power t minus I into s power n, where both b, t and s are real numbers. Now in this case, this is the equation. If we get this kind of equation, what should be the solution? The particular solution should be, now here we have two scenarios. The two scenarios are, suppose this s, which is some real number, if this is the root of this equation, okay, so suppose we have 3 over here and 3 is a root in this case, for this equation we generally find the roots, right? For this equation, if 3 is the root, then we have second case, when 3 is not a root or s is not a root, then we have the first case. So when s is not a root of the characteristic equation, this is your characteristic equation. So this is the first case. When s is not a root of the characteristic equation of the associated, this will be your associated linear homogeneous recurrence relation. If you remember it from the earlier topic, that is theorem 5. So in theorem 5, we divided our equation into two parts. One was the associated part and the other was the particular solution, an of h plus an of p. Then when s is not a root of this equation, then the solution will be of the form I is equal to 0 to t pt minus I n power t minus I into s power n. Now the second case will be when our s is a root of this characteristic equation and its multiplicity is m. Then there is a particular solution of the form n power m. So this term is added as extra. n power m I is equal to 0 to t pt minus I n power t minus I into s power n. Okay, so this n power m is the multiplicity when s is a root. So if s is repeated once, then it will be n power 1. If s is repeated twice, n square and so on. We will see a few examples for understanding this, but for now you have to remember that theorem 6 will have two cases. One will be when if s is not a root, the other will be when s is a root. Whenever s is a root, to the case 1 we will just add n power m, where m is your multiplicity, that is how many times the root is being repeated. Multiplicity, or I'll just write it over here, multiplicity means how many times the root is being repeated. Okay, so that is the multiplicity. The factor n power m ensures that the proposed particular solution will not already be a solution of the associated linear homogeneous recurrence relation. So n power m is basically ensuring that whatever our solution is, it is not already a solution. Okay. Now, so this actually is the textbook slide of your theorem 6, or the textbook content of theorem 6. So instead of writing it in the sigma format, it is all expanded over here. Suppose that En is equal to C1 An minus 1 plus C2 An minus 2 plus and so on up to Ck An minus k plus f of n, where C1, C2 and Ck are all real numbers, and f of n is equal to, what is f of n? It is b subscript t n power t plus this bt minus 1, b1, b0, all of these are real numbers. So these are just simply constants. What is important is this: we are raising n to the power of some t minus 1 and so on. Now, when s is not a root of the characteristic equation of the associated linear homogeneous recurrence relation, so this, then the particular solution, this is for case 1. Okay. pt n power t plus pt n minus 1 n power t minus 1 plus and so on up to p1 n plus p0 into s power n. Okay. One more thing. If you have in our problem n and some constant, then we will have only p1n plus p0. If we have all these terms, then we will be taking all these terms. Okay. That is, if we have suppose n square plus n plus 1 into 7 power n, suppose, and 7 is also the root of our equation, then we will write this p2 n square plus p1n plus p0 into 7 power n. This is how it is written. Suppose if s is not a root of our equation, when s is a root of this characteristic equation and its multiplicity is m, then we simply multiply with n power m to this case 1. So this will become your case 2. Okay. So I hope you have understood this. It is a bit confusing, but we will see an example and then it will be clear. So let's see an example for the same. So for this, the example is, what form does a particular solution, let me write the question. Question is, what form does a particular solution of the linear non-homogeneous recurrence relation an is equal to 6an minus 1 minus 9an minus 2 plus f of n have, when, in this we have a few cases or a few sub problems. So we'll see the first one and we will see as we go to the next one. F of n is equal to 3 power n. Okay. Now, what is the associated linear homogeneous recurrence relation? This will be the associated homogeneous recurrence relation. So let's mention that the solution associated linear homogeneous recurrence relation is an is equal to 6an minus 1 minus 9an minus 2. Now, what will be the characteristic equation? It will be directly I'm writing. You can do it step by step as I have shown you in theorem 1, I believe. So directly it will be r square minus 6r plus 9 is equal to 0. And that can be written as I minus 3 whole square is equal to 0. The roots are real and equal. R is equal to 3. Both are not R1 and R2 is 3. That is, the roots are real and equal. So in this case, it has a single root. Let's mention it over here. Our problem has a single root. What is the root? 3. And how many times we have? It is being repeated twice. Okay. So the multiplicity is 2. Multiplicity is 2. Now, what is the equation? 3 power n. The root is 3 and this is also 3. Okay, this is our s. If you remember from our general formula, then this is the s. Now it has to apply theorem 6 with f of n of the form p of n into s power n, where we have the polynomial and s is a constant. We need to check whether our roots and the equation is the same. So that is same because s is equal to 3. So this I'll just write it over here. S is equal to 3 and R is also equal to 3. Both of them are equal and the multiplicity is 2. So we have to use the case 2. Case 2, if you remember, let's see the case 2. When S is the root of this characteristic equation and its multiplicity is m, we have to use this case. Now, do we have any of these terms in our f of n? No, we don't have. We don't have b0, b1n. We don't have any constants associated with 3 power n. So if you see our problem, we simply have 3 power n. So that means when we are writing the solution, we don't need to have any of these terms except for p0. Why? Because we have 1 into 3 power n. If we take it as a product of polynomial and the nth power of a constant, then we can take our formula as 1 into 3 power n. So hence, if we are taking 1 into 3 power n, we have to take p0. So our solution can be written as, the general solution or the particular solution of our complete equation is given as multiplicity is 2, so n power m into, since we have 1 into 3 power n, we are simply taking p0 into whatever s power n we had. So we are taking 3 power n. Multiplicity over here I have given as 2, so our equation will be in the form, general equation will be in the form p0 we have to write first because it is a constant into n square into 3 power n. This is the general solution. Once again I am saying that since we do not have any polynomials n except for the constant, if we consider 1 into 3 power n, that is why I am taking only one term over here, which is p0. Okay, now we will see another example. Suppose for the same an is equal to 6an minus 1 minus 9an minus 2 plus f of n, but in this case our f of n is given as n into 3 power n. Now if you see our this term, the term 3 power n is being multiplied with the polynomial n. Now what will be the equation? So the equation or the general solution, so our root is the same 3 and this 3 and this 3 are the same, that is s power n is the root of the characteristic equation and the multiplicity is also given as 2, which we have already found out in the earlier problem. Now f of n is equal to n into 3 power n. What is n into 3 power n? If we are taking this as n into 3 power n, if we want to compare it with our formula, it will be this way, b1n into 3 power n. So what did I say? If you have n, the nth term or the n term, then we have to take two constants in our solution. So if we are writing the solution for this problem, we will have two constants. We will have P0 and P1. So and also n power m. So if I want to write the solution, n power m into P1n plus P0 into 3 power n. Why am I taking two terms or two constants? Because we have n over here. So we have to take two constants. If we have n square, we'll be taking three terms. If we have n power 4, you will be taking four terms over here. So you get the gist of what I am saying is, whenever we have n power whatever over here, so if we consider 1, it was n power 0. So we were taking only P0. If we have n power 1, we will be taking two terms. Okay. So I hope you have understood what I am trying to say. So n power m into P1 n plus P0 into 3 power n, or it can be written as, what is the multiplicity? It is 2. So n square into P1n plus P0 into 3 power n. Okay, I said if we have n power t, we will have n power t plus 1 terms in this bracket. Okay. In the earlier case, I said t terms only, we will have t plus 1 terms. All right. Now, in the next example, let's see the next example. The same problem, instead of f of n being n into 3 power n, f of n is over here is n square into 2 power n. Now, our s is given as 2, while the root of the equation we got was 3 and the multiplicity was 2. And s is given as, I'm sorry, I said s is given as 2. S is 2, root is 3, so we have to consider the case 1. Now you have got the case 1 problem. What is the case 1? When S is not a root of the characteristic equation of the associated linear homogeneous recurrence relation. Now, if we see over here, 2 is not a root of our equation, earlier equation, which is given as 6an minus 1 minus n 9an minus 2. The root for our equation is 3, while s is 2. So we have to consider the case 1. That is, we have to take n power, we should not be taking n power m. Okay, we should not be taking n power m. So let's see the case 1 once again. Before seeing the case 1, we will see that we have n square over here. So totally how many terms we will have in the bracket? We will have 3 terms. And let's see this. We have to write P0, P1 and P2 also, and we should not be multiplying with n power m, how we usually multiply when s is a root. So let's write the general solution, and for these problems you can write it directly. This won't be essay problems, this will usually be short answer questions, so you can write it directly. So for this n square into 2 power n, your general solution will be P2n square plus P1n plus P0 into 2 power n. This is your general solution. Okay. Now the next thing is, when we have our fourth f of n is given as n square plus 1 into 3 power n. If we have n square plus 1 into 3 power n, then in this case, if you see 3, s is given as 3, that is this, and r is also 3, and what is the multiplicity we have? Multiplicity is 2. And we have over here n square plus 1. So n square plus 1 means we have the highest degree is 2. So totally how many terms we will have again? We will have 3 terms in the bracket. So for this, the general solution will be n power m into P2n square plus P1n plus P0 into 3 power n. What is m? The multiplicity is 2. So this equation is written as n square into P2n square plus P1n plus P0 into 3 power n. Okay. So this is the general solution for our this n square plus 1 into 3n. Now, For theorem 6, the initial conditions will not be given. This is the only thing we have to find out. So that is the reason I said this will be in FAQ or short answers question. Now this concludes the topic solving linear recurrence relations. But before I conclude the topic, what I would like to do is I would like to revise all the theorems that we have studied till now. So for that, let's see. I've made this sheet. Actually, this is like a cheat sheet to get all these theorems in one place, so that whenever you have an exam, you can easily remember the characteristic equation and also the general solution. So if you remember theorem 1, we have studied a long while ago. So I hope you go back to those topics and revise it. So first and foremost, we have theorem 1. So these 1, 2, 3 denotes the theorem. So theorem 1 is C1 and C2 are real numbers. Okay, C1 and C2 are real numbers. In that case, our characteristic equation will be R square minus C1R minus C2 is equal to 0. Okay, and suppose if I take an example, our equation may be given in this way: an is equal to an minus 1 plus 2an minus 2. Then we get the characteristic equation in this way. What will be the characteristic equation for this? R square minus r minus 2 is equal to 0. Once again, I am saying that I am doing it directly. If you are supposed to do it, I'll show you over here. So over here, if we have the equation an is equal to an minus 1 plus 2an minus 2. How do you find the characteristic equation? First, you shift all the terms to the other side and make it equal to 0. an minus 1 minus 2an minus 2 is equal to 0. Then what do? You write it in powers of r power n. Okay. So r power n minus r power n minus 1 minus 2 into r power n minus 2 is equal to 0. Then you divide this entire equation with the lowest power of r that you have over here. So you will divide it with r power n minus 2. So once you divide this with r power n minus 2, you will get, so this n minus n plus 2, a power m by a power n will give us a power m minus n. I hope you remember this, exponent and power. So this n minus, when this power goes to the numerator, the signs will change and we will have over here r square minus r minus 2 is equal to 0. This is how you get the characteristic equation. I hope you remember this from our earlier theorems. Okay, so I may have probably taught this in only theorem 1. The same methodology needs to be followed for all the theorems till theorem 6. Okay, so now once you get the characteristic equation, depending upon the roots, we will be choosing our theorems. If the roots are distinct, what does distinct means? We have two different roots, r1 and r2. Then our solution will be, general solution will be given as En is equal to alpha 1 into r1 power n plus alpha 2 into r2 power n, where alpha 1 and alpha 2 are constants. Okay, so if alpha 1 and alpha 2 are constants, then our general solution is given in this form. And if you have initial conditions, then you can even find the value of alpha 1 and alpha 2 by using the substitution equation methods that you have already studied. Now, in the same case, C1 and C2 are real numbers. Characteristic equation is given as follows. But instead of the roots being different, we have equal roots, as we have just seen in theorem 6. That is, r was equal to 3. Then in that case, we will have the solution as alpha 1 into r naught power n. Okay, so first is similar, but for the second term, we will have alpha 2 into n into r naught power n. So the same root is being multiplied by alpha 1, but in the second case, we will also multiply it with n. So alpha 2 into n. So this term is being changed from theorem 1. So if we compare theorem 1 and theorem 2, then this second term is different. What is the difference over here? We are multiplying the second term with n. Okay, this is in the case of equal root. So let's again summarize, if we have distinct roots, our solution will be alpha 1 into r1 power n plus alpha 2 into r2 power n, the simplest solution. If we have equal roots, we have to remember that we have to multiply an is equal to alpha 1 r naught power n. In alpha 2 should be multiplied with n and then again the root whole power n. Okay. Now, theorem 3 is if we have distinct roots more than 2, that is if we have 3 or more distinct roots. Okay. So if we have C1, C2 and Ck as real numbers and we have k roots, suppose k different roots, then our equation will be how many ever roots we have. If we have 3 roots, we'll be taking 3 constants. So let me just write here alpha 1, alpha 2 and so on up to alpha k are all constants. Okay. So if C1, C2 and Ck are all real numbers and we get k distinct roots, then R1, R2 and so on up to Rk are the different roots, then each root should be multiplied with a constant. It will be alpha 1, alpha 2 and alpha k. Now for the next theorem, which is the fourth theorem, if we have multiple roots and they are being repeated. So the term multiplicity is if the root is being repeated. C1, C2 and Ck are all real numbers and our characteristic equation is given in this form, that is it will be a polynomial equation with degree 3 or more and R1, R2 and Rt are all the roots, okay, where R1 is being repeated m1 times, R2 is being repeated m2 times and Rt is being repeated mt times. Then our solution will be alpha 1 comma 0, how many ever times it is being repeated, we have to take those many constants and r1 power n. So suppose our r1 is being repeated 3 times, then we have to take alpha 1 comma 0, alpha 1 comma 1 and alpha 1 comma 1 into n plus alpha 1 comma 2 into n square. Okay, we have seen a problem with respect to this theorem, please refer back to that. So this is the formula. If R2 is being repeated only one time, then we will simply take alpha 2 power 0 into R2 power n. Okay, that is the theorem 4. Now theorem 5, usually whenever the theorems are asked in LAQs, we usually get theorem 1, theorem 2, 3 and 5 in LAQ and very rarely we get theorem 4 and 6. So theorem 4 and 6 are not very common for LAQ. While 1, 2, 3 and 5 problems based on these theorems 1, 2, 3 and 5 are very important. That is, if you are getting a question from unit 3, 80% chance that you will get one of these problems. Okay. So this recurrence relation solution is very important. Apart from that, you will get generating functions. Generating functions also is an important topic which is related to again this topic. So my point is that this topic, solving linear recurrence relations in unit 3 is very important. Okay. Now the next thing is our theorem 5 which we have seen. An is equal to, so this is for linear non-homogeneous recurrence relations, and while you are taking the solution you have to assume over here for f of n, and this is a little bit difficult, so you have to solve a few problems based on this theorem. And what will be our solution? An will be equal to an of p plus an of h, where an of h is the associated homogeneous recurrence solution. Okay. Now over here in theorem 5 needs to be practiced and you will have to see the various cases. That is, if we have a polynomial, what is the particular solution that we take, and if we have a constant with power n, then what is the particular solution that you have to take. I've shown you both the examples in the theorem 5 session, please refer back to it. Now the next one is the theorem 6 which we have just seen. Theorem 6 is basically when we have f of n as a product of polynomial and a power of nth power of a constant. Then in this case we have two cases. We have just seen the two cases. Now one more thing is In my important question list, I have given all these recurrence relations problems with respect to each theorem. So I please practice all the problems in such a way that you will be able to solve any problem, and these problems are usually given entirely for 7 marks. Okay, so whenever you get this problem, if you do it correctly, if you understand the concept, it is very easy, and if you do it correctly, you will get the complete 7 marks. Important for both internal and external. Hope you have understood the topic. If you have any queries, you can email me. Thank you.